चलेगा फर्स्ट बेंच
नहीं, फर्स्ट बेंच पे
कुछ करके रख दो। ऐसे कितना टाइम लगेगा?
ऐसे पकड़ लूँगा ना, हो जाएगा।
So, in the last class we have seen how to transfer the slab load to the beam. Okay, if you are not interested in modeling the slab explicitly, so this is the way you can do. Okay, and why you do this is to simplify the model so that it can run faster. But suppose most of the people in industry they use the shell element for slab modeling because it's easy. You do not have to calculate the load and each member separately and it takes a lot of time. Okay, so to avoid those things, you may sometimes want to do that, and we'll see how to do that. Suppose now just imagine we do not have any load applied because of the slab in this model. Okay, we are freshly trying to do that, and in this case, what we do first we'll go to define, then define slab section, and only one slab definition is there, but still I'll show one definition. You can name anything whatever you want.
बना दिया क्या?
Let's say it is 150 mm. And deciding this whether 150 or 100 or let's say 200, it will depend on the requirement, how much you want. Okay, how much flexibility you want in the slab and whether the slab thickness provided is sufficient or not. Okay, so those will be the part of design. We are not going to discuss those things now. Just tell me it's 150 and see for the time. And here you see you have few properties, and this you have already learned in aerd. What is shell beam, what is shell beam. Then you have membrane and you have layer. Layer is again it is shell. Okay. But there is a definition of membrane and shell, and I guess all of you know what is the difference between membrane and shell. Okay. Now, if you are assuming your slab to be rigid in place, okay, and it is not taking any out of plane action, that time you can model it as a membrane. Okay. But suppose you want to simulate the behavior because of out of plane action also, that time membrane will not work. Okay. You have to go for shell. It means if you are using shell, it will cater both the purposes. It can take what is the purpose of membrane as well as the outer plane action. Okay. And in shell, if you are taking shell in, so you are ignoring the shear deformation behavior. Okay. But if you are taking the shell thick, so that will be considered. It's up to you what you want to simulate. Normally, we consider this one. Okay. Because out of plane stiffness, whatever is provided by the slab, that is very much negligible compared to the other members. Okay, so it will not have any significant shear deformation. And I think this you have already learned when you have studied the basic RCC course. You have designed the slab, and normally in case of slab design, we do not explicitly check the shear check. We just inherently assume that it will be safe. Okay, so this is the reason you can go for the shell thing. So now definition is done. You can assign the slab now. Here you can select all the stories. If you have similar slab definition to all the stories, yes. Then here you have three options which you can use for assigning slab. Okay. Each one will have different advantages. You can explore this. Let's try this. And here you have to select slab. You can just click each of these panels. by doing this, what happens? It also draws a slab at the base. Okay, so this you have to do it now. Here you just check this one story, and you can go to plan. Now you can select all these names. So this is the way you can model. Now if you want to assign the load, this is what I wanted to show you. If you model the slab like this, how to assign the load. Now in this case, see the dead load of slab is already done. Okay, you have modeled the slab, so you do not have to consider the dead load again. But this is what we have done in the last case, because in that case the slab was not modeled. So dead load we have converted to a line load, then transferred that to the surrounding beams. But in this case, that you should not do again. Okay. But other loads, the floor load, live load, floor finish, and any other kind of load which is acting on the slab, means floors, that you have to assign here. Now let's say I want to assign the live load. So I can again go to all the stories, assuming that the live load will be same in all the floors. Okay. And you can select all the slabs. Then go to assign shell loads. You have to go to this shell loads, and you can select this cleaning form. और आपसे कुछ बात ही करना था, कुछ नहीं कर लेते। Okay, so I think that was 3.5 kilometers per meter square. So now you understand why people do that. Okay, it just took maybe 2-3 minutes. But same thing if you want to do manually transferring the load to the beams, it will take maybe hours depending on how much large your model. Okay, so this is why people like to do this, but there are several negative factors with this. I will not say negative, it's like lack of understanding. Okay. If you are using this model, you should have proper understanding of how it behaves and what are the factors you have to take care of. Okay, but people do not understand all those factors, but they should supposed to understand. Okay, simply they use this modeling technique and transfer the load because it gives them advantage compared with respect to the time. Okay, so you should not do that. You have to understand in which case which one should be used. Now this is the way you can again apply different kind of loads. I will not go to show again all those. The procedure is same. Just type of the load will be different. Is it clear? Now another thing is meshing. If you are doing this one, another thing which is very much important and very much ignored by the people. Okay, depending on the size of the meshing, this we have discussed in the FEM class also. In one day, how the size of mesh fits the behavior. We have seen that. Okay. So same thing is applicable here also. Okay. So when you are modeling using shell element, you have to take care of the meshing. Proper mesh test should be provided. If you want to do that, go to assign, then shell, and here you have to select floor auto mesh option, and see, if you do not do anything, it is considered as default, and here you see under this default what happens, and you can read this text. This is the setting that will be used on all shell flow objects object machine unless another choice is specified on this form. Following are three categories of shell objects used to determine the default settings. Which one is used depends upon the properties of the shell object and its orientation. Okay. Horizontal depth and plans are usually auto cookie cut at beams and wall meshing options because these types of flow objects do not have out of plane sequence. Vertical loads are transferred from the floor and to the beams and vertically tributary conveyance algorithm. Then horizontal slabs and layer slabs use the automatic rectangular meshing or the meshing as specified upon the automatic mesh options. For slabs with magnetic behavior, vertical loads are transformed to vertical support and then close. Okay, we have to check the second option. It is saying that if you do not do anything, it will consider general meshing. Means software will automatically assign some mesh. Okay, so that we do not have any control what kind of mesh will be assigned. So better to go with our own understanding. Okay, if you are relying on software, at some location maybe it will provide rectangular meshing, at some location triangular meshing. It will combine all this because it's just a computer algorithm. It will automatically do something. Okay. But if you want to assign your own meshing, then you click on this, then decide this how many elements in X and how many elements in Y. And here you can select the last discussion we have seen if you are providing some 8 by 8 meshing, then it's sufficient. Okay.
सर मैशिंग का एक्चुअल मतलब यूज़ क्या है सर?
Meshing, use of meshing, right?
यस सर.
See, if you do not mesh, the element is like rigid in entire dimension. Okay, so its stiffness becomes very high compared to the actual stiffness. So as you are meshing, making it finer, so that whole element will be divided into small blocks. So stiffness will be divided. Now the stiffness will be different compared to the unmeshed one. Okay, and if you are making the finer and finer, so stiffness will be close to the actual one. And actually it affects the final behavior. The result, if you compare unmeshed and meshed one, you will see the final result will be different. You can without meshed. So if you want to check your mesh, you can go to this form, clicking on this button, then select this shell analysis mesh, then OK. Now you can check. Okay. This is a mesh provider. And another thing is, in the last model we have also defined rigid diaphragm. Remember? Now, if you use this shell element technique, okay. Suppose you are modeling the membrane behavior. Okay. In that case, you do not have to go for rigid diaphragm. But if you are modeling specifically shell behavior, in both the case, same element you will be using. Okay. Hello. 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 This one.
शशिकांत
अरे इसमें भी क्लास लेने का मन नहीं है.
शशिकांत मैशिंग कहाँ से आता है?
असाइन असाइन
सन में कहाँ से?
असाइन शेयर उसके नीचे जाओ. वाई फ्लोर ऑटोमेश ऑप्शन
कहाँ पे है? मैं सब्जेक्ट तो 8x8 पर है.
लास्ट क्लास तो नहीं आया, फिर बनाया कब ये सब?
लास्ट क्लास थोड़ी ना मैंने बनाया,
फिर ये पुराना है।
ये पुराना है।
तो
उससे
लास्ट क्लास में क्या करवाया भाई?
वो लोड के थे सब, जो था ना 12 लोड के थे सब, वो सब करवाया।
अच्छा, ये तो मेरे पास भी होगा शायद।
शशिकांत, एड रेस्ट्रेंट्स ऑन कॉर्नर मानना है, ये करना है, एड रेस्ट्रेंट्स ऑन एड्स ऑफ कॉर्नर्स।
Add restraints on edge if corners have restraints.
पता नहीं किए थे कि
नहीं किया
नहीं किया था ना। करने से क्या होता है?
रेस्ट्रेन ऐड हो जाएगा,
restrain add होगा corners में
फिक्स्ड हो जाएगा मैश।
लाई,
तो फिक्स्ड होना चाहिए ना।
हाँ वही तो हो गया।
corners में वो बोल रहे हैं additional restraint डाल।
भयंकर चीज़ है भाई ये सब।
मेरा भी दिमाग में नहीं है।
Okay, so the rigid diaphragm, when you are modeling the membrane, you do not have to go for rigid diaphragm. Okay, because the purpose of membrane is to simulate the in-plane behavior, and we assume that the in-plane stiffness of this entire floor diaphragm is very much high. Okay, so if you do not provide the rigid diaphragm, also it will act as a rigid diaphragm. But suppose you are modeling the shell element, so purpose of modeling is to simulate the out of plane behavior also. In that case, it will be little bit flexible compared to the membrane element. Okay, so in this case, you have to again define the rigid diaphragm. Okay, so now it depends on what you are trying to model. Same kind of element. By looking at this, you cannot understand whether rigid diaphragm will be required or not. Okay, that as a designer you have to understand. Now in this case, since we are modeling the shell element, so we have to define the rigid diaphragm also, and that you can do by selecting the entire model. Select this one, and you have two options. One is using the area definition, another one is using the joint definition. Okay, normally we do the joint definition, so that you can do. Go to assign, then join, then diaphragm. Okay, and here you select this. We have seen in the last class. Clear? So this is something different what you have to do when you are dealing with this shell element. Now let us go back to our model. We will work on that. So in the last class we have seen the analysis. Up to here we have done the last class. So today we will see the design and how to check the result. See, before going to the design, in this phase you have to satisfy some criteria as per the code. Okay, the first thing you have to do is to check the motion, means modal response parameters. Okay, whether the time period is satisfying the criteria given in code. Okay, two time periods means two consecutive time periods should be away from each other by at least 10%. Okay, that is one check you have to do. Then another check is the mode participation factor. Okay, minimum mode participation factor should be achieved is 90%, including all modes. Okay, and the first three modes should be at least 65%. So these are the few criteria given in code that you have to check. So this you can do by clicking on this display, then go to store tables, and here you select one is base reaction is base shear, and these are the modal parameters. Basically we require these firstly, remaining also you can check if you want. See, so this is the first mode period and it is acting in y direction. Okay, and the first mode participation is 81.96%. Our requirement is at least 65 for three modes. Okay, So this is satisfied in the first mode itself. So it is good. Then the second mode is in the x direction, and again participation is more than 80%, so it is satisfying the criteria in x direction as well as in y direction. Okay. Now if you check the summation of three modes in each direction, okay, don't read from here because it is for both the directions. You have to read for each direction separately. Okay. So this is three modes for y direction. If you add, the summation is shown here, 95.53%. Our requirement is to satisfy 90% for all modes. Okay. So here it is better. You are achieving that target in first three modes itself. Okay. Similarly, for x direction, if you add, it is giving you 95% again. And if you add total, almost 100%. We have included total 45 modes. So for each degrees of freedom, 15 modes. 15 modes. 15 translation in x, 15 translation in y, and 15 torsion. Okay, so total 45. Now, including 15 modes for each direction, you are achieving 100% mass participation. So there is no loss in mass participation. Okay, so this is possible only when you have a simple model. But if you are using like lot of irregularities in your building, so it will be very much difficult to achieve at least even 90%. Okay, so it's very difficult. But your target should be always to get the maximum possible. Okay. So this is one thing. Then base shear you have to check. Okay, this is base shear, and see, this is RQX means response spectrum load case in x direction, and this is response spectrum load case in y direction. Okay, how much you are getting? 625 in x and 616 in y. Okay, now this you have to compare with the equivalent static. Okay, and if it is less than that, you have to scale it. That is called base shear correction you have studied. Okay, let's check how much you are getting in equivalent static. This is equivalent static method in x direction, and if you see, it is giving 2069. Here you have three steps because if you remember when you define the load case, let me show you once again. See, we have checked these three boxes. For each one of these, it is giving the result. Okay. Now, if you have lot of irregularities, you will sometimes identify difference in the result shown. But if suppose you do not have any irregularities in the model, so it doesn't matter whether you are selecting or not selecting. But to be on the safer side, you have to check all this. Hello. मैं अभी क्लास में हूँ क्या है? Okay, so you see in the three steps is giving the same result. Okay, that means there is no problem with the model and there is no eccentricity also. If suppose there was significant eccentricity, you would have got the different result. Okay. Similarly, this is for y direction, this much. Okay, and again because of the different time period in x and y direction, you are getting the different result here. And now this should be means the response spectrum result should be matched to this equivalent static result. Okay, so this is what you do in the base pair correction. Okay, now how much this scale factor, that we have to decide from here. Okay, you just divide this higher value with the lower one and get the factor that will be used in the scale factor. Okay, check how much you are getting for each direction. Three point 304 for x and for y. So here we have to multiply 3.30 with the existing scale factor. Okay, and how much you are getting for y? 2.71. 7. Okay, so like this you have to apply the base share correction. Now suppose your response spectrum result is higher than equivalent static. Are you going to multiply the reduced factor or you don't have to do anything? Okay. Although it is not going to happen, just hypothetically I am saying, if you get a situation like that. Okay, but suppose you get sometimes, then you have to definitely cross check your model why you are getting that. Maybe it is correct, but possibility is less that the model will be correct. Okay, because in that case your response spectrum model will be stiffer than the static load case. Okay, which is not going to happen anyway. So if you are getting anything like that, then definitely you have to check the model properly. So okay, this is done. Then again you have to run the model. Then you can go to remaining check. One is to check the drift limit. There is a limit given in code. If you remember, can you tell me how much that
0.4%. 0.4%.
Okay. So it means 0.004 if you are removing the percentage.
The 0.4%.
So that you have to check here maximum storage drift and check the load.
0.4%.
Now for checking the drift, code gives you the criteria what load case you have to use. Okay, it says unfactored load. It means if you see the load combinations, there is a factor 1.5, 1.2, 0.9 something like that. Okay, so when you are checking the drift, you do not have to use the factor, only the actual load case. Okay, it should be the design basis, means design level artifact, not the 1.5 into z. Okay, it will be 1.5 into z divided by 2. Okay, for that code case you have to check. Now that is and response spectrum load case. Okay, this I think was discussed in class. When you are calculating the force, it will be governed by the equivalent static load case. That is why we scale our response spectrum forces by a factor to match the static load case. But when you are checking the drift, it will be governed by the response spectrum, not the equivalence tab. Okay. Because here, if you plot the displacement spectra, you have seen in your assignment also now. Okay. The period is longer. Okay. So the response spectrum load case will give you the higher displacement. Now, just cross check, we will compare these values. You are getting this much. Okay, before that, let me once again check the base shear whether they are same or not. So this is the response spectrum base shear and this is the equivalent static base shear. So now you can see they are almost matching. Okay. Similarly, this is for y direction and this is static case y direction. So response spectrum and static load case are giving the same values. So our correction was fine, and now we'll compare the drift ratio using both the methods and see what is the difference. This is static load case. Here you see how much you are getting. Maximum is 0.00729. You can read the values at the bottom of the curve. Okay. 0.00729. Okay. So this is from equivalent static load case. And if you go to the response spectrum load case, zero point 00718. So it is giving the values which is lesser than equivalent static. Okay. So it is contradicting the understanding. What we understand is response spectrum should give the higher load, higher displacement. But here it is happening opposite. I don't understand this. Okay. I think what happens is since you are increasing the forces, although it should give the higher displacement in response spectrum, but that force is, again, if you are applying the force, it will give you the displacement also, right? So that additional factor is coming from there. So both are matching. I don't know, I don't understand it completely.
Drift is maximum at story level load.
Sorry?
Maximum drift should be at maximum should be
Should be.
maximum displacement from the building should be.
This is not displacement, that is the difference. This is the drift.
Interstory drift.
What is the difference between?
Drift is the relative displacement between two stories.
Interstory.
Okay.
Yes.
Suppose
ये बताएगा शेल थी का
what you have to check for drift, this limit should be less than 0.4%. Okay. And now see, here I am checking only one load case. I am not adding the gravity load case like dead load, lag load. But as per the code, you have to use all the loads. Why I am not adding this? The gravity load direction will be vertical. It will not contribute significantly to lateral load. But you have to use that also. So what you do, you make one combination dead load plus live load plus earthquake load without considering the factors. Okay. So you have to check this for that load case. And now, okay, let me show you, and you'll understand the difference. Go to combination and make another combination. Let's say drift combination. X. So that load will be full, then slab that load will be full, flow finish will be full, then you have that one. Then you have live, and then we use the earthquake load case. Okay. So this same thing you can do for both static and dynamic load case. Okay. So you make another combination for now I am using the dynamic load case, means retrospective load case. Same thing you can do for equivalent static load case also. Similarly, you just copy this for other direction. GUI and rest of the things will be same. Now you can go back and check the result. See, now I am checking the displacement as I was showing in that diagram. You can see the displacement pattern. It is maximum at the top. Okay, but if you identify the relative displacement, the drift is when you are calculating the drift, you have to calculate it as like this displacement, story displacement divided by height of the stories. Okay, that will give you the drift. See, I am checking for this combination, but there is no change in the result. Okay, but this may not be the case if you have a like tall building, let's say 30 to 40 stories, and you have a huge plan area and lot of complexities and irregularities. That time here you will have some difference, but not significant load. Still, that difference you have to consider. Okay, in this case, model is small. You do not have a large model, and there is no irregularities present in the model. That's why you are not getting this difference. Okay, but you have to check this for combination, not for a single load case. Okay. What else we can check? So these are the preliminary check before going for the design. So when you satisfy all these, whatever you have done, then you can go for the design. Before designing, you have to check this. See, we are going for comic frame design. Okay. This is your code book IS 456-2000. Then number of interaction curves. You know PM interaction, right? Studying.
Column.
So it is asking how many interaction curves you want to use. Okay. So by default it is selecting 24 interaction curves. So if you divide 360 by 24, you'll see at what angle this interaction curves are plotted. Okay. Then number of interaction points.
So this one is for making PM interaction curves, sir.
No, this is for design, but in design PM interaction will be used. So it is asking you for that PM interaction, what are the criteria you want to choose.
Sir, why did you write 24 number of interaction curves there?
I didn't write, it is given by default.
By default.
By default.
If you want to use any other number, you can enter here how many interaction curves you want to use.
Sir, it means each column in that figure, but sir, many number of columns were there.
This is not for column. Okay. See, you take one member, you
Yes,
have
sir.
two orthogonal directions, 90 degree apart. Now, this is giving you 24 interaction curves. Means this 360 divided by 24, you see at what angle you have this capacity curve.
Oh yes.
Okay. It is not taking only two directions. It is taking multiple directions at a particular angle. So minimum acceleration we have considered in our load case. Then additional moment. This as per IS 456 there is a clause of additional moment depending on the slenderness ratio. So that we are deciding whether to consider or not. Then P delta, this we have done in our model. Design for beam curve, capacity ratio, okay, the rest of the things. And this is another thing, you know, gamma of steel 1.15 and gamma of concrete 1.5. 75, just leave it. This is not as per our code actually. And next we have to click on this design communication. See, now I don't have all the combinations figured here, okay? But before designing, you take all the combinations, how many combinations given in code, that will be preparing. And once you have done, means defined all the combinations, it will be shown here, okay? So whatever you want to select for your design, that you can just check and click on this, so it will be shifted to this right side box, okay? So whatever combinations you are providing in this right side box, that much will be considered for the design. Okay. Now since I have only this many, we'll consider this many. But you have to do according to whatever you want from the code. Okay. Then now you can start design. So design is done, and first thing you have to check is whether members are failing or not. There is a preliminary check here. Go to this option display design info and identify all failures. Okay, so it will give you some preliminary check. I think it will be better if we go to illustration. Okay, so I think it is visible.
Sir, PMM means
Yeah,
PMM, sir. That
PML. So wherever there is a failure, it is giving this kind of information. Okay, it is not written whether failure or not. You have to understand. If suppose something is written, it means it is failed. Okay, so these members are failing in PML. So now you have to understand what is the meaning of that PML. Then only you will be able to rectify that. Okay, so PML means the size whatever you have provided is not sufficient to resist the movement whichever is coming to that member. Okay, so you have to increase the size, and also the reinforcement what is provided, that is not sufficient to carry the movement. Okay, so the solution for this is to increase the member sizes. Clear? Yes.
We have not provided any reinforcement, but whatever reinforcement it takes.
No, it has designed. Reinforcement is designed, but again reinforcement will depend on the size also. Okay, so it has given some reinforcement. You have limit. Reinforcement should not be less than a minimum value. It should not be more than a maximum value. So now the maximum whatever is given, it will be related to that maximum given in the code. It cannot go beyond that. So you have to increase the size so that reinforcement can be increased. Then let's see any other failures are there or not. So all members are failing in PML. It means we have to increase the sizes on the bottom stories. Whatever 5 or 6 stories you have failure, and the correct way is to go to each of these member, then increase the size. Okay, rather than increasing the sizes for the entire structure. Okay, so that will be very much uneconomical. So now to make the thing simple, we'll select all those entities together. Okay, but it will not give you economical design. So when you are designing for a real case, then take care of this. Okay. So instead of 400, let's say we will make it 550. Now again you have to check the ratio because you have changed your structure, so ratio will be different. Again you have to apply the ratio correction. See, now the response vector load case is giving you 2571 and the static load case is giving you 2233. So what do you do? Whether you are going to apply the ratio correction or not?
No.
No? Okay. You have to apply because this is not the real case. This is because we have already applied the correction and made the changes in our structure. Okay. So in this case you have to apply.
Oh yeah.
आगे
काम ही बहुत ज़्यादा थोड़ा
चलता है.
Okay, now we'll remove that scale factor and see how much correction we have to apply. By default it was 9810. So we'll check with this. Now you can see this is given by response spectrum load case and this is given by the static.
Static.
So how much you are getting the factor?
2, 2, 3, 4, 9, 7, 21, 3.5.
Okay.
2.8.
2.86. This is for X, right?
पीछे वाला देखिए. शील्ड है.
2.86. And what about Y? One eight five two divided by 769. Two point four one. Now you can run the circuit. Okay, it's done. Again, if If you want, you can go back and check your review. Now see, your structure became stiffer, so the result your drip ratio reduced. Okay, this is what you should expect, right?
Yes. The straight is reduced. 0.005.
No, I think it's increased,
Increase. 0.
not reduced.
Initially it was 0.002.
Point double zero 5 to 0.0052, right? Earlier it was 0.00. I was thinking 0.000.
That
It
was
means
your-
it's exceeded the limit. The limit is 0.004.
Yes, sir.
Yes, sir. Accident.
Yeah, it exceeded. So I was thinking it's 0.000 something. So I thought it's not exceeded. Okay, fine. So it means we have to make the structure stiffer. Okay. So still it is not satisfying the criteria. So I think we
मैं
can
समझ
have
गया।
the rigid diaphragm.
शेल थीन शेल थिक इन प्लेन आउट सब डिफॉर्मेशन देता है
We have to
लेकिन मैं प्लेन
because
से
we are
इन
not
प्लेन
modeling
देता
the
है मतलब डिफॉर्मेशन को
mandate,
रेजिस्ट
so
करता
we
है
have to define the rigid diaphragm. It's done.
ये आउट ऑफ प्लेन है ये
Okay,
प्लेन
so
कैसे
we have to increase the member sizes because the drip criteria is not satisfying. What we can do is let's increase the size of beam also little bit. Instead of 500, let's say 600. So one thing what you understand is the designing of building is not a single step process. You do multiple iterations, check if the criteria is not satisfying, again you go back to your initial state, then do some modifications and carry on. So this should be done until you are reaching the final objective. Okay. See? 0.0043. So now, what we can do is, since we have seen for the design, upper stories were already satisfied. Okay, but unnecessarily we have increased the member sizes there.
Yes, sir.
Okay, so if we reduce the member sizes on the upper stories, it will make the structure light, means the mass of the structure will be little bit reduced. Okay, so the drift will be reduced little bit. Okay, so that is little bit cumbersome. I have to identify, separate the members, then it will take time. So instead of doing that one, I will increase the size for the entire structure and see what happens. Before that,
0.004.
we have to apply the base rate correction. So now the response spectrum is giving you 2932. Because of this one, actually, you are getting that. There are some unnecessary extra forces. 2932. 0.81. Now you can see 0.0033. Okay. So that forces, because we have increased the member sizes, so it attracted unnecessary extra forces. Okay. Similarly, in this direction also 0.003. So it is within the limit, and now you can go to design. Now you can see we do not have any warning message here. Okay, so your member is passed. Right? Now check whether the reinforcement, whatever is designed by the software, is within the reasonable limit or not. Okay. What it is so is you have one minimum percentage given in the code, another maximum percentage given in the code. So anywhere between the minimum and maximum will be considered acceptable by the software. But in general, what happens? As per the code, the maximum reinforcement percentage in column is 6%, right? So we do not want reinforcement to be near to 6%. Okay, 5% or 6% is not very much suitable amount of reinforcement. Normally, if it is between 2 to 3%, so it is a very good estimate. Okay, so we will try to keep the reinforcement in that range, 2 to 3%. Okay, and similarly for beams also. In case of beams, if the percentage is 0.5 to 1.5% in that range, so it is considered a very good estimate. Okay, so if the values given by the software is coming within that limit, then we will consider the model as acceptable. Otherwise, we will revise that. Right? Okay, before that, one more thing, sorry, I forgot to discuss this one. You have to check the beam column capacity ratio. This you have studied in aerd.
Beam column.
The ratio, I think it was discussed in class, right? How much is that value, beam column capacity ratio? 1.4. Okay. So we'll check this, how much you are getting in this design. You have to check column to beam capacity ratio.
Strong column. दादा कुछ हो ही नहीं रहा है।
in one direction, see, this column, if I consider this column, it is connected to two beams. Okay, so that's why you are getting two values. Means one is for x direction, another one is for y direction. As per the requirement, it should be more than 1.4. So here you can see it is more than 1.4 in one direction, means 1.8, another direction it is very much high, 8.4. So that much is also not required. You try to keep in between 1.4 to 3 maximum. Okay, but it is very much difficult. As you can see, this member in one direction it is very much reasonable, another direction it is very much higher. So why? Because I have provided a square column. So capacity is same in both the direction, but demand is different. So instead of going for a square column here, you can go for a rectangular column where you need the minimum, where you can give the shorter dimension. Okay, so this you can do. So like this, by checking these values, you can optimize your members. Wherever you need, you increase. Wherever you do not need, you decrease. Okay. But in no case, it should be less than 1.4. So here we do not have any warning, so this clause is satisfied. Now, depending on how much you want to keep, you can estimate and optimize your member sizes. Okay. Then what else you can check here is, okay, the failure we have seen already. Then let's check the reinforcement percentage. Okay, so the bottom score is giving you, this is for one of the grid line, bottom story column. Here you can see the requirement is coming to be 1.14%, which is very much reasonable, 1 to 3% as we discussed. But from the second story onward, you see the requirement is 0.8% and it is constant throughout the height. Okay, what does this mean? Yeah, this is minimum reinforcement, but what insights you get from this, whether your members are sufficient or under designed or over designed. Okay, so if you keep this design, there is no problem with the performance. Okay, it is better than what you need as per the code, but the thing is it is uneconomical. Wherever you see minimum percentage is showing, it means your size, member size, whatever is provided, it is more than what we need. That much is not required. Okay, so it will be uneconomical if you provide this. So based on this observation, you go to that member and reduce the sizes. Okay, so there are multiple things you have to take care of. This is from the point of view of economy. If you want to save on the economy, and this is the main factor for the designers in industry. Okay, you know the design and you are not taking care of all these things, so you will not be able to survive, because ultimately you have to save on economy. Right?
So this one is showing minimum percentage of steel, sir.
Yeah.
So but minimum percentage of steel is 0.8 or 0.18%.
Yeah, so 0.8 is showing, right?
0.8.
0.8%. Okay. 0.8% means your concrete area is means it is very huge. That much is not required. That's why the steel requirement is coming this much low. Okay. So you have to provide a reasonable size so that the reinforcement is also within the reasonable range and the member size is also reasonable. Okay. So this you can do. And when you are reducing the sizes, again you have to check the drift ratio also. Okay, both the things should be considered. So I am not going again to reduce the sizes and check. You know the procedure. When you are doing for your work, you take care of these things. And similarly, you can check for beams. You can go to plan now. Okay, now see, in case of beams I told if the percentage is coming to be between 0.5 to 1.5%, so that is a good estimate. Okay, but now here you see it is coming less than, no, I think it's fine. Here you see at the top the requirement is 0.71% and bottom 0.48, so almost 0.5. Don't look the values at the center because it is always it will be minimum. Okay, check the values which is near the support. Similarly, this end if you check 0.66 and 0.48, so it's okay, acceptable. Similarly, this also if you see acceptable, this is acceptable. So in this storage, if you see x direction, all the beams are acceptable. Means reinforcement is within the acceptable range. But what about y? Which is less than 0.5. Means in y direction you can reduce the sizes little bit. Okay. So you do that and cross check once again what is the requirement coming. Okay. This is how we also check. Similarly for another storage. So this is also same thing, x direction fine, you can keep the sizes whichever is provided, and y direction you can revise. And like this you can check for all your stories. Okay. So from the 12th story onward, you can look into both the directions and reveal the member sizes and check again. Okay. So these things you can do with respect to design. Okay, there are many things, optimization, then checking the good criteria, all those things. So finally, after doing all those things, then you will finally arrive at the final design, which will satisfy all those conditions and make the structure economical. Okay, so after that, once the design is completed, then you go for the nonlinear analysis, if at all it is required. Okay. In industry, people do not do nonlinear analysis because one thing is they do not understand how to do, another thing is they do not want to do because it takes a lot of time. Okay, but since you are in the art engineering department, this is the thing you should learn, and we'll see nonlinear analysis.
Next.
I think today we'll skip, and from the next class we'll start the nonlinear analysis discussion. Okay. And by that time you can practice all these things. Make a final design. My design is not final. Okay. Make a final design with all the things whatever we have discussed, and next class we can discuss the result. If you want to discuss anything related to the reinforcement, how much we are getting, then whatever code criteria you have to satisfy. So if you want to discuss anything before starting the nonlinear analysis, we can do that. But at least practice this one. Otherwise, whatever I told will not be that much useful if you are not practicing this.
ये सब भी चाहिए लिखते हुए ना मैं
Yes. Read out.
Sir,
पेन देना भाई
once your mass source gets P the calculus, so
Mass source, right? Okay. You want to see this combination? Yeah. So mass source is dead load 100% and live load if it is more than 50% and it is less than 3 then 25%. Now we have provided 3.5 km per meter square. That's why here factor is 0.5, that means 50%. Okay. Anything else?
Sir, when you were designing and you mentioned about the AML failure, so we had to go to we had to put columns individually and then change the position.
Yeah, that is the most ideal condition. You go to each member, then provide a suitable sizes, then check again. But if suppose you have a small model, it is possible. Go to individual member and provide the sizes. It's very much difficult for complex and large structure. So what you do, you group the members together. Like either you can take one grid for a single size, or else you can take like all the corner columns and make in a single group and provide the same size. Like this, you can make the groups and provide the same sizes for those particular groups. Okay. Similarly, along the height also, like from bottom to 3 stories, I will provide a single size, then 3 to 5th story, another size like that.
You can reduce the size as you go.
Yeah. It is better thing to reduce the sizes as your height goes up, because it will reduce the mass of the structure, so the force which will be attracted will be less. Any other questions?
If we reduce the size, how the reinforcement will be?
That you have to check out from design.
Like from bottom to, if section changes, if it reduces, the rebar will be in different positions from top to.
Okay, means you are talking about detailing. No problem. When the size reduces, means the joint you are talking about, right? Suppose bottom story I have 500 by 500, immediately on top of that you have 400 by 400. So how the reinforcement will be continued? That is your question. You can provide little banding, that is acceptable, no problem. Means where that size reduction occurs, at that point you bend the rebar little bit, so bring it little bit inside, then continue upward. But this size reduction again, it should not be like drastic. Okay. For example, in one story you are providing 1000 by 1000, immediately on top of that you are providing 400. So in that case, the band requirement will be used, that will not be acceptable. You can reduce by let's say 50 mm per reduction. Okay. So that is not significant if you are reducing 50 mm.
Also, there is soft story. Soft story में जाएगी उधर.
Soft story.
ये हो जाएगा और उधर डिफरेंस होगा स्टिफनेस.
हाँ, वो हो जाएगा. फिर भी मतलब अगर नहीं भी हो रहा है फिर भी नहीं करना चाहिए.
सर लेकिन जब हम रीबार को ऐसे बेंड कर देंगे तब तो सर वो वहाँ पे बकल नहीं होगा सर, क्योंकि बेंड तो पहले से हो चुका है सर. जब लोड पड़ेगा उस पर
पहले से नहीं बकल मतलब अंडर आर्टिफिशियल एक्शन यू आर टॉकिंग.
अंडर ग्रेविटी एक्शन ही, मतलब वो बकल नहीं कर जाएगा सर, क्योंकि सर जब रीबार ऐसे बेंड होके जा रहा है फिर तो सर.
That's why it should not be significant. Up to 50 mm, let's say, it is acceptable. Nothing will happen. In normal situation also, when you are providing the slicing, what you do? You bend.
स्प्लाइसिंग.
Okay. Then like one bar is coming like that, another bar is coming like that. Then you join connect together, right? There also you are providing this kind of bending. Okay. So if the requirement of bending is less, it will not affect the